So, last talk on FAUST of this conference. It was supposed to be yesterday afternoon before the talk of Romain Michon, but we had to exchange with Victor. So this is the reason I am alone to do this at this time of the conference. So the point here is try to explain again the architecture file model of FAUST, since we obviously continue to extend it to develop the FAUST ecosystem. And we want to share some techniques we find useful to design reusable components at the architecture file level. And also get around some current limit of the compiler. In particular, I will explain how we can deal with sample accurate control even with the current version of the compiler. The thing is that when we look at way of the external developers sometimes use FAUST, I mean, not writing FAUST code, but using the architecture file model to embed the FAUST-generated code into their plugin or system. We sometimes see strange things like generated code, C++ generated code that is later on cut into slices to be embedded in additional code. And we think, or I think, sometimes it's not the way to go, and maybe it's only because the way we think architecture file can be used is not enough understood, and maybe this is the time, after 15 years, to explain again the way it's designed. For example, guitarists, they are using the FAUST compiler, they are generating code, and they are using additional script to cut part of the generated code to put into their final product. Well, maybe it could be done in a simpler way. So what we are going to explain in more details is also the way we can do with the polyphonic support in FAUST. It was already presented a bit by Romain yesterday. How we have extended the system to be able to deal with MIDI messages, control with MIDI. So, starting from the beginning, at the source level, FAUST program basically describes the DSP computation itself, the way samples are going to be processed or generated. And part of the source code basically describes the connection with the external world by means of controllers, which could be a graphical user interface, usually, but also any kind of control messaging system you may want to use, like MIDI, OSC, or even sensors, accelerometer, when you deploy a FAUST code on a mobile platform, for instance. So we have a kind of a notion of abstract UI, which basically describe controllers directly into the source code. So you have here an example of FAUST code with two sliders. So, one is controlling the volume and the frequency of an oscillator. And for instance, the volume slider has a label, some additional metadata that you may use if you want to control this slider with, in this case, MIDI. In this case, you see that the volume slider can be controlled later on with MIDI controller 7, which is a volume, standard MIDI volume. And so this code is later on processed by the FAUST compilation chain. There is the compiler produces a C++ class. and then, which is a kind of standalone C++ class that has to be connected to the external world so that you can process audio samples, and so that control of the DSP is connected to actual control of the external world. So the model we have designed 15 years ago is something like that, with those three parts. The DSP code is actually the blue part. Then you have to design and use the audio driver module that connect to the audio chain, and the control module, or the user interface in this case, which basically describe how you are going to control your DSP. So if you look at how this kind of concept is described at the code level, so we have a base class, which is the DSP class, with a set of methods, and this is the class, the shape of the class, which is going to be generated by the FAUST compiler. In particular, you have the getNum input and getNum output functions that will return the number of input and output of your DSP. You have the compute method, which is going to compute the actual DSP. And you have this build user interface, which is the generic way to connect your DSP with a UI star, so a UI interface, which is a pointer on a UI that we will see later on, which is a generic way of building the user interface. Now, obviously, we have this base class. Here on this picture, you see that the compiler may produce an actual, for instance, karplus DSP by compiling a karplus.dsp source file and producing a karplus C++ file. But obviously, we use the same hierarchy of class of DSP. So we have subclasses of the DSP base class. For instance, when we use libFAUST-based dynamically generated DSP, the compiler will actually produce a LLVM DSP object that is a subclass of DSP that will be usable in exactly the same context like the statically compiled DSP. And then you have additional classes that we have designed over years, like this PolyDSP class that will be the way to build, by combining several voices, a polyphonic object. And we have this new timed object, timed DSP, that will allow to do sample accurate control, and some way of doing kind of macro construction, like putting two DSP in sequence with this DSP sequencer class. So basically the idea here is that in some case you may want to build separate DSP by combining by compiling separate source code and then combining at the C++ level and not combining them at the FAUST level. This is the point of having a separate C++ class to do sequential composition that you would obviously you could do at the FAUST level, but we will see later on in which context having this kind of tool could help. Now, if we look at the definition of the UI class, this is a set of methods that a UI class may have to define. So the class will have possibility to add buttons or sliders or new entries that are defined in the source code of the FAUST program, and possibly you may also define some kind of abstract layout at the FAUST level, so that you want to group your UI elements in horizontal layout or vertical layout or tab layout, this kind of thing. Obviously, this is graphical UI-based approach, but you may define a class that implements those methods, but that do not have any graphical meaning. For example, if you want to connect your DSP with the OSC, you will not exactly have to implement the notion of grouping you would do on a user interface. And then, obviously, over the years, we have developed several classes so that you can deploy the same DSP source using, for instance, a Qt framework or GTK framework, so that you can have the same source code running with different GUI framework, or if you want to control your DSP with OSC, you have to use this OSC UI class. Or you may want to control your DSP with a pure console text-based, so you don't. Then you may use this console interface. At the audio levels, then again we have a base class, so that any audio driver will have to implement this function, those function. Especially the init function that will take the actual DSP. You have a start and a stop function and some additional function you will have to define when you want to implement an audio driver. So we have developed several audio drivers so that to be able to connect the DSP onto ALSA, core audio, power audio, jack, net jack, and some more drivers that have been developed since. So now, if we look at an example of a FAUST source, and if we look on part of the generated C++ file, you see here the compute method that does actual computation, and what you see also on this picture is the build user interface. So the build user interface in this case is generated by the compiler for the source we saw just before, and ask the UI manager to open a vertical box, another vertical box inside, add an horizontal slider, then a button, close the box, and all the lines that you see on top basically trigger the UI to build the actual user interface. And assuming that you compile it with the different UI managers that we have, you will have this kind of output. If you compile it with FAUST to CRQT, for example, on OS X, you will have this display and jack and GTK support on Linux, for example, on the right. Now, concerning polyphonic support, as Romain explained yesterday, obviously you could describe polyphony directly at the FAUST level, but in some cases you want to have simpler polyphonic support, and then you just want to use FAUST to program the one voice of your polyphonic instrument. And we have defined conventions so that you have to use frec, gate, and gain labels into the controller that will actually control the frequency, the gain, so the velocity of the voice, and gate will be used to trigger on-off the note. And there is also another convention that allows to describe the maximum number of voices you may want to use into your object. And then you look at what Albert Graf has already done. And I mean, well, Albert already did a lot of work to do polyphonic support, basically on LV2 and VST plugin. So what we did recently was taking part of this approach and trying to put it in a more generic and reusable component. And so we have designed a Poly DSP class as a subclass of the base DSP class that does, as you would understand, voice allocation and note handling and voice stealing and this kind of thing. And that will be later on connected to MIDI or OSC if you want to control your polyphonic object with MIDI or OSC. The point here in this approach is trying to keep the shape of the DSP class. So basically it means that in this case we have decided to extend the build user interface method so that a polyphonic instrument may have a bit more complex user interface, and so that you may want to access each voice of your object. So we decided to do that by using a tab group layout, and we add a master voice so that you can, if you need to, control all the voices at the same time. For example, if you want to change a parameter on all the voices at the same time, it's quite useful to have at the graphical user interface level a kind of master to control everything. So it means in the implementation of the Poly DSP class, we have this kind of code that will basically wrap the build interface, user interface of the actual voice that will be put into this polyphonic object, and that adds some more control with this master voice concept and this panic button, for example, that will allow to cut off all the running voices if you need to. But the point here is to understand how we try to push for this kind of extension of the DSP class, in this case, an extension of the build user interface concept. So it means when you build polyphonic instruments starting from a karplus syne kind of voices, you will have this kind of GUI with this master voice, and possibly the fact that you can access to individual voices. Here you see two tabs with voice 1 and voice 2, and you may want to click to voice 1 and voice 2 and possibly change or arrange something at the voice level, but obviously, usually you will just change parameter at the master level. And the fact that you have this hierarchy that has been built extending the build user interface means that when you think about the OSC control level, when you are using the mono object, you will have the kind of path you have at the top of the picture. And when you start your object in polyphonic mode, then you have an additional level in the hierarchy, so that you can, if you need to, access to individual voices. And if you go a step further by using this effect model that also was already described by Romain yesterday, you may want to add a global effect to your polyphonic objects. So you use this effect, you add effect into the FAUST something script. And then this is a case where we use this DSP sequencer class that connects the polyphonic object with the effect object, which are each one compiled separately by the compiler as two separated C++ classes, and which are then connected as a C++ level using this DSP sequencer class, which is one. Now, sample accurate control. I have first to explain the way control and DSP interact into generated code. So we have a very simple model since the beginning of the FAUST project. We basically, the compiler generate for each control, we basically have a single memory area to transfer data between the DSP and the control. So basically it will be a float that will be written by the control part, and that will be sampled at each block of the computation and kept constant during the entire block. This is the model we use currently in FAUST. And the way it's sampled is just because in the generated code, you can look at the compute method in this case, starting from the source code where you have a slider here. The actual value of the slider is taken once per block outside of the DSP loop and just put into a local variable into the compute method outside of the DSP loop, and then the f_0 value is kept constant, obviously, during the entire duration of the block. So this is a simple model, but it has some drawbacks. For instance, the fact that the DSP part only sees the last value of that was actually written on the memory zone. So in some cases, you may lose, the DSP part will not see all values, all control values, which is not a problem in most cases because you are only interested to get the last value of the control. But in some cases, obviously, it could be a problem. Like if you decide to, for instance, we had a use case, we had to solve this use case. If you want to synchronize an audio algorithm described in FAUST with MIDI clock, then you have to receive a stream of MIDI clock with sample accurate timestamping, and obviously you want to count each clock because the tempo in the MIDI clock model is the series of all clocks and their timing difference. So you cannot afford to miss some clocks when you want to synchronize a mini clock stream. So obviously we have to do something special because the actual model of the architecture and compiler cannot do that in a clean way. So we have designed a kind of decorator-like DSP, which is named time DSP, that will actually decorate an actual DSP produced by the compiler, but that will put in place a more complex way of dealing with control value by keeping them all and having all of them get a timestamp and keep all control value in a queue. And this time DSP basically is going to have a bit more complex compute method. Instead of having a compute method done on the entire audio block each time, you will have to actually cut the compute into several slices so that you are sure that you take the state of if control which change during a given audio block. So you just need to keep all the message, have their timestamp, and do this kind of computation where, in this case, you have an example with 4 slices of different sizes, and for instance, the V1 control changed 4 times into the audio block during the audio block, and the V2 control changed 2 times, and the V3 changed, as you understand how it works. So it means control changes between slices. So it's a bit of a hack, but it was a way to have this MIDI clock control running and working at sample level correctly. Concerning MIDI, we have we have designed MIDI messages, MIDI meta messages, so that you can decide to have your button or slider be connected to MIDI messages. And we have also defined the three messages that you need to deal with MIDI clock synchronizations, also the start-stop message at the clock that basically deliver a sequence of 1 and 0 each time a clock is received. So basically it gives the FAUST code a square signal running at changing each time the clock is received. And so having this square signal synchronized with the MIDI clock stream, then you can, at the first level, derive an audio signal from that. And this is an example of a simple code that would compute an oscillator which frequency is synchronized with the MIDI clock, the speed of the MIDI clock, in some sense. So we just have to detect each front of the square signal, measure how many of those front you have during 1 second, and then from that you can derive the frequency. And this force code, when you connect it with MIDI support, so that you will have a frequency controlled oscillator controlled by the MIDI tempo, which is quite funny to have. And obviously, since as soon as you have a this MIDI square signal, you can do everything you need. And for instance, the SuperDirt guy, Vince, he designed several tempo-based audio application and loop control application for his work using this kind of approach. So the MIDI part, also at the low level, we have a kind of hierarchy of MIDI classes with a base class and several classes that map to the native API. We use RTMIDI for multi-platform support, and we have specialized classes for Jack, Bella, which is a nice low latency audio card, and also Juice, so that we can connect with the Juice framework, for instance. This MIDI and polyphonic support has been added into part of the FAUST2XX script. Basically, you have additional parameters. And also, since the idea was to have a kind of generic class, we can deploy it also on FAUST Live, FAUST Gen, and even on FAUST web tools. Perspective, we have to work with Albert to extend this polyphonic development, since Albert has done a lot more into VST and LV2 plugin. So we want to merge all this code into a single concept at some point. And obviously, at the first level, we have to think about how we want to connect the DSP control if we want to be sure in this kind of application when you need to have timestamp and the control value, how we can do that at a more deeper level into the FAUST generated code. So, very short demo. Just showing how this polyphonic support works into, for instance, FAUST Live. Here I'm launching FAUST Live, taking an instrument, compiling on the fly using the LLVM-based libFaust dynamic compiler. And now I just need to activate MIDI support, activate polyphonic support, change the number of voices. And now we are in a case where we use a polyphonic class which is fed by this LLVM DSP object. So the user interface change a bit. You have this master-like voices with a panic button tab. And here you have a MIDI input so that you can connect you can connect your MIDI control to control the polyphonic object. And you may want obviously to we can have the same polyphonic support in Max for. So we have this in FAUST with a new polyphony parameter so that you can change dynamically the number of voices you want to allocate, just to wrap the single voice which is described in the FAUST editor. Yes. So nothing special, but well, again, it was just to make. Again, a description, a more full description of how it works and how it's supposed to be used, so that you developer, if you want to develop new architecture file for FAUST, we try to use the same kind of design. Ça va? Content?
Thanks a lot, Stéphane, for your presentation. Are there any questions in the room? Nope. Oh, yeah, sorry. And Harry took.
Hey, Stéphane. Interesting stuff on the parameters and to see that flexibility from FAUST Live. It's not one I was familiar with, but really impressive. Apart from that, I'm curious on parameter mapping. So Yann and I were actually chatting earlier, and I think it would be interesting to see how can we expose. So the architecture files allow us to expose the internals, like items that are in the FAUST DSP code, but to make those even more user-friendly from various different surfaces. And to try and kind of discuss how we can genericize that to some degree. I think there's some value there to try and make things more accessible in general, I think. So although I would absolutely agree the architecture files are a very good way of achieving a specific implementation. So if you want to interact with a MIDI device or with OSC, to go beyond that and make things slightly more dynamic might be a nice direction to take.
You mean in relation with what you are designing with?
Yes. So with hardware controllers and integrating from hardware controllers to FAUST and trying to get a mapping working there between those things. Exactly. Yes. Thanks.
The comment. A thing we are working on is the idea that, as Stéphane showed, we use metadata inside the name of a slider. Obviously, if you start to have OSC messages, MIDI messages, control A messages, etc., then you have a very long name, so it's not more usable, so to speak. So the idea is we will decouple, separate a little bit the metadata from the actual name, so that you can just use in the real source code the actual name and have a description of how the metadata apply to the various names. So you can have using pattern matching ways to have a very flexible way to code the metadata. So maybe we can have full description of devices, like with Control A, and apply a full description to a FAUST code.
So a kind of CSS for
Exactly.
The FAUST source,
Yes.
something like that. Yeah.
This may be a bit unrelated, but still, as you modified the polyphony settings, how does FAUST react when you set it to polyphony 4 but play 5 notes? Does it have some note stealing algorithm?
Yes.
There
is a standard note stealing algorithm. Right now, it's probably stealing the lowest volume or thing like that. Yes, it's stealing voices. Yes. But we can also improve this kind of algorithm because you may have different way of deciding which voice you want to steal in this case.
Okay, we still have time for some more question. Anyone? Okay, thanks a lot, Stéphane.